Churchland, Peter Singer, Steve Pinker, Simon Blackburn. And then we just did one recently, I'm looking at the homepage now, on What is Life, with Richard Dawkins and a few other people.
Great venture.
Again with Lawrence. So he's, as director of this Origins initiative at ASU, Arizona State University, he's been doing amazing things. We're enjoying collaborating with him enormously. And he also came to the meetings that we did called Beyond Belief. We've done Beyond Belief 1, 2, 3. And they were at the Salk Institute, and we talked about those sorts of issues about science, religion, reason, survival, and so on. So it's great to have him here. As he will tell you, he likes to be thought of as a public intellectual, and Scientific American described him that way, and that's reasonable. I think that's a term of endearment, not a term of abuse.
Oh, yeah.
In this
Some people.
Country. So I'm delighted that he's here. He's actually. Before he was doing this, he was at Case Western University. I mean, you can look him up on Wikipedia, obviously. But the important things that I like to point out are that he's actually now co-president of the board of the sponsors of the Bulletin of the Atomic Scientists with my old friend Leon Lederman. And in 2010, he was elected to the board of directors of the Federation of American Scientists. So Lawrence, and the reason that I support him so much is that he does God's work. And I'm talking about Spinoza's God, Einstein's God, but he does God's work. And I must read this out because you obviously want this to be known. He's the only physicist ever to have been awarded the highest awards of all three major US physics societies, the American Physical Society, the American Association of Physics Teachers, and the American Institute of Physics. He's a great communicator of science. I think you're in for a wonderful evening. And I must tell you one last little story, which is the last time I saw Feynman. I went to a birthday party for somebody called John Lilly. Any of you know John Lilly? Yes. Dolphin work and so on. And I remember going into the house up in Decker Canyon in Malibu, and walking into the house, and Feynman was playing bongo.
Sounds like it.
Feynman was playing bongos. Thank you. And John Lilly was walking around in a dressing gown, talking to the television set, because there were entities in the television set. And that was when John was in his vitamin K, ketamine phase, so it was very interesting stuff. But Lawrence will now regale you with some more stories about Richard Feynman, but mostly about Richard's kind of scientific life. This is another biography. It's a very interesting book.
It is a biography. It's just.
I enjoyed reading it enormously. So over to you.
Thank you very much, Roger. Thank you. Let's hope this. Okay.
One other thing, because it is being recorded by the Science Network, I need to say, quick disclaimer, could you actually turn your cell phones off or put them on stun or something? And the other thing is, if you're here with somebody you're not supposed to be with, or if you're running away from the IRS, now's a good time to leave.
Uh-oh. Okay, well, thanks, Roger. It is indeed a pleasure to work with Roger, and I'm glad this is, and my friend John Booth, who's behind the camera as well, who's worked with us on many occasions now at the Origins project at ASU. In fact, next week, just so you know, I'll do an advertisement. If you want to drive up to Tempe next weekend, we have a major event, a 4-day event of celebrating science and culture, which the highlights of it will be on Saturday. We're going to have a performance of Holtz the Planets with images from NASA, narrated, it turns out, by me, and then followed by a lecture by my friend Stephen Hawking, who will be there. And then on Sunday, we're having another friend of mine, and I know Roger's, Anthony Grayling, coming in the morning to talk about his new secular Bible. And in the afternoon, another friend, Werner Herzog, will be there with his new 3D film, Cave of Forgotten Dreams, which is a remarkable film, truly remarkable. And we'll have a panel with Werner afterwards. And then on Monday, we're going to have a dance event with the MacArthur Prize-winning choreographer Liz Lehrman called A Matter of Origins, which is an interactive dance event. So I recommend you consider a nice weekend in Arizona before it gets too hot, and consider coming by to see those events. Anyway, enough for advertising. I wouldn't have done it if Roger put me in the mood. Okay, but this is not. Well, I was going to say it's not about me, but it's about Richard Feynman. But of course, as my if this is being recorded, I was going to say as my soon-to-be ex-wife, but she'll watch it. I know anyway. It's always about you, Lawrence, and it is. And so here is a picture that some of you can see. Richard Feynman has played an important role in my life for a long time, well before this. Happens to be a picture that was taken when I was an undergraduate. I'll talk about it a little bit. And I happen to actually have been talking physics with Richard Feynman at that time. But Richard Feynman came into my life, as he does many physicists, as a student. In fact, it's kind of interesting. I first heard of him when I was at a summer science program, and I was kind of bored. And the teacher saw me bored, and he said, I want, and remember this story because it's relevant, because it's something very similar happened to Feynman. And he said, I can tell you're bored. Here's a book by this guy, Richard Feynman. And it's really neat. He shows that antiparticles are particles going backwards in time, and he just won the Nobel Prize for this, and you should read it. So it was the book, a very famous book of his, which in fact is for sale here, I noticed right there, The Character of Physical Law, which was a transcription of lectures, the messenger lectures that he gave at Cornell. They're a beautiful volume, and I highly recommend reading them. But at the time I read them, and they inspired me. I didn't understand them. I found out my teacher didn't understand them either. He didn't quite get it right either, as I'll describe later. But what they did for me was, for the very first time, make it clear to me that physics was kind of dynamic. It was actually alive. I'd learned physics, and I'd learned about all the great scientists, and I kind of figured it was done. And here was someone who, I was told, had just discovered these wonderful things about antiparticles. In fact, he discovered them 30 years earlier. But it convinced me that maybe it was worth becoming a physicist. There was still something left to do. And then, of course, when I was an undergraduate, I did what every undergraduate does. I bought these books here, the Feynman Lectures on Physics, the Bible, the Red Book, also right there, I think. Is that those them? Yep. And every student buys them, puts them in the room, doesn't understand them, but periodically looks at them for inspiration. They were truly the first of their kind. It was a complete redoing of all of introductory physics, and not so introductory physics, from a completely different perspective, which was just, of course, typical of Feynman. And like many students, I kept them, and then when I was a graduate student, I began to understand them, and still have them and work with them today. But then when I was an undergraduate, I was fortunate enough to be involved in this association called, I grew up in Canada, called the Canadian Undergraduate Physics Association, which invited well-known scientists to come up and lecture to ostensibly the best undergraduates in Canada, and I was later president of that. In fact, I got John Wheeler to come up, but this year there was a very beautiful young woman who was president, and she somehow convinced Richard Feynman to come up. She actually flew down to Caltech and walked into his office unannounced, and lo and behold, Feynman showed up, and I got, this was after his lecture, but it turned out we spent the weekend together because I was there with my girlfriend, who was one of the only other women there, and Feynman spent most of the time with us. And I'm happy to say, although I guess I was going to say I didn't want this broadcast, but it's okay. No, it's okay. The message will get out. So Feynman taught me how to dance, and so I can thank him for that. And so that was fine. And then I met Feynman. Well, I did my PhD at MIT, and when I was at Harvard after that, Feynman used to come to Boston periodically and lecture. But then once I went to Caltech and gave a colloquium after I moved to Harvard, and Feynman was in the audience, which was fairly intimidating for a young person. And he asked an interesting question, got right to the point, and then after the lecture, he came up. He wanted to talk more, and I was itching to tell him. I knew he probably wouldn't remember me as this young student he'd met a bunch of years earlier up in Canada, and I wanted to tell him all about it. But this really annoying assistant professor, who I'm happy to say did not get tenure, would not stop asking me questions, and finally kept standing there so patiently, and finally just gave up and walked off. And I thought, okay, well, I'll get to tell him another time, but Feynman died shortly thereafter. So I never got to tell him that, which I've always regretted. And I was particularly happy when I was asked to write this book for this series called Great Discoveries. Because, first of all, I figured I could read all Feynman's papers. One thing that most people don't realize about physics and science is that you don't read the original papers. They're usually... the great thing about science is it gets redefined and re-expressed in ways that are ever simpler. And it's often incomprehensible to read the original work. And like many people, I hadn't read Feynman's original papers. I'd read one or two. But I thought this would be an opportunity, it would be a motivation for me to actually read the papers, which is why I agreed to do it. But I also wanted to do it because there's been a lot of books, and many of them are here on this table, about Feynman the character, and Feynman the prankster, and Feynman the joker. But not about Feynman the scientist. And Feynman was a scientist first and foremost. He may have been a joker, but when it came to science, he was deadly serious, as I'll describe. He, in a sense, became the conscience of physics. And I wanted to describe his science. And I thought, in fact, I could use his life, which is incredibly interesting, as a hook to explain the science. Much like I wrote a book, The Physics of Star Trek, and I use Star Trek as a hook. Because people might not be motivated to learn the science, but if they learned it through Richard Feynman's life, they might. And in so doing, get an introduction to 20th and 21st century physics. Because as I'll describe, Feynman worked on things that eventually are the basis of everything we're working on now. So I'll give you, I'll talk for a while, probably longer than I should, about some of these things. And then I'm happy to answer questions. So here's Feynman as a little child. And when he was there, you probably would, when he was a kid, the question I asked myself first is, would you have known he was going to become one of the greatest physicists of the 20th century? And I think the answer is probably no. He was a pretty regular kid. He was a smart Jewish kid from Long Island. Okay, and he did things. He had a chemistry set. He did some things that were kind of spectacular. He had this radio repair business. And Feynman was also, besides a scientist and a joker, he was a showman. And anyone who ever heard him lecture and saw him lecture realized that he was a showman, or even when he was being interviewed. And I think it began very early. He had this radio repair business back in the days when radios were tubes. And he was famous because in the neighborhood because he fixed radios by thinking about them, which was his motto. So, and there's a very famous story told about this one time when this radio guy came in with this radio and plugged it in, and it just shrieked endlessly and disturbed everyone in the neighborhood. And Feynman paced back and forth for 10 minutes thinking, and then went up and switched two of the tubes in there and fixed it. Now, I am certain that he knew right away what the problem was. But even as a 10-year-old, he knew how to play to the audience. And that was one thing that was evident early on. The other thing that was evident early on, which is also not too often stressed about Feynman, is, you get this idea that he just came up with these miraculous ideas and could solve any problem, which he could, but sort of on the spur of the moment. He liked to preserve that mythology, actually. But he was incredibly methodic in his working of science. He worked endlessly and rigorously and kept voluminous notes, thousands and thousands of pages of notes, but it began early on. As a 12 or 13-year-old, he went to the library to get a book called Calculus for the Practical Man. And he had to tell the librarian it was for his father, because they believe it was for him. But, and you can see his notes here. Even as a 13-year-old, his notes on Calculus for the Practical Man, rigorous, organized for himself on integral calculus, just to work through that. Just characteristic of that. The fact that Feynman was able to work intensively on a problem, focus endlessly until he solved it in an organized fashion, or two key factors about the man that are not often appreciated. But what got Feynman interested in physics was an episode which was somewhat similar to the episode I described with myself, although I don't in any way intend to make any relationship between the two of us in that regard. He was bored in high school, and his teacher, Mr. Bader, came up and gave him, told him about something which he said he fell in love with, and he remembered ever since. It was actually called the principle of least action. But first, but to get there, I want to describe something which is interesting called the principle of least time, which was something that was discovered by Fermat, a mathematician who's known for something else. For Fermat's last theorem, he scrawled a theorem in the margin of a book and became famous, not because he scrawled the theorem, but he scrawled the claim of a proof of a theorem that took 300 years for people to solve after that. But Fermat actually did some things as well as make some claims. And one of the things he did was explain a property of something we teach and we bore students in physics class. We teach students, I don't because I find it boring, but we teach students optics, and we teach them something called Snell's law. It sounds boring already. It's just the fact that light, when it goes from one medium to another, bends. And it bends inward if it goes from air to water. And we can tell students, we can even give them the formulas for how much it bends, and they memorize it, and they think that's how physics is done. You just, someone tells you something, says it's right, don't ask me why, and memorize the formula. which is of course not how physics is done. Well, that's true. That's how light behaves. But you can understand this from another perspective, which in fact Fermat showed, which is really amazing and far more interesting. That is, well, you can't quite see it that well with this, but imagine light when it leaves this laser, wants to go from here across the street. Well, what it does is it thinks about all the different paths it could take, and it chooses the path that takes the least time to get there. And that's the way it behaves. Now, of course, it goes in a straight line across the street because there's just nothing but air between me and the street. But you see, if you have air and then water, the light travels faster through air than water. So if it took a straight line, it would travel longer in the water than it might if instead it chose to spend more time in the air and then bend and then go as close as it can to vertical in the water. And you can calculate all the different paths that light will take. And you will find the path it takes by Snell's law is the path that takes the least time. So light figures it out and takes the path of least time. Well, it doesn't, but it behaves as if it does. And that's a fascinating thing. And one of the things I'm sure that fascinated Feynman about it is he was fascinated, as am I, by the fact that you can express many physical laws, ways that seem totally different, each one revealing something different about nature, yet they all produce the same predictions. But this is an amazing fact. Now, in fact, in Arizona, if you drive there, you may see a mirage. And this effect is responsible for mirages, and I couldn't resist explaining mirages for those that have never seen them. So, a mirage, of course, when you look at the street, you look down at a hot highway way ahead of you and you see what looks like a puddle. Or if you're in the desert walking, you see what looks like water. And the reason is, what's happening is the light comes from the sky where it's blue and comes down, and it might just hit the ground, but it doesn't because if it's very hot, there are many layers of air above the ground. And at each layer it bends, and it bends outward because the air is hottest near the ground and less dense. When it goes from more dense to less dense, it bends outward. And so it bends outward until it finally makes a return path and comes up to your eye. So you're looking down on the ground and you're seeing light that comes from the sky. That's how we normally explain it. But in fact, you can understand it using this principle of least time, because the light has two choices. It can come from the sky directly to your eye, making a straight line through the air. But this air up here is cold, and light travels slower in cold air. So what the light instead decides to do is go down and hang around as long as it can in the hot air, and then come back up to your eye, and that takes less time. So the principle of least time is why they're mirages. Now, Feynman was not told about the principle of least time by Mr. Bader. He was told about the principle of least action. The principle of least action sounds like a government agency or something, but it actually is something else. It's a little more complicated, but I'm going to show it to you because you're a sophisticated audience. I'll show it to you not in extreme detail, but I want to actually show you the equation. First, I want to remind you of something that you may have learned in high school. When I throw something up, it has two different kinds of energy. It has the energy of motion, something we call kinetic energy, which is always positive. It has potential energy, which is the energy it gets for the potential to do work. If I drop this on your head, it would do work on your head. So by lifting it up higher, it can do more work, and so it has potential energy. And it has the sum of these two things. Now, it turns out Newton told us how things move. But there's another way, completely different, that will tell us everything that Newton told us. If we just to say that when a particle goes from one place to another, it takes a path that minimizes the action. So there's kinetic and potential energy. And what is the action? The path it takes, some path, is determined by the sum over the path of the difference between the kinetic and the potential energy at every point. So a particle always tries to make sure its potential energy is as close as possible to its kinetic energy at any given point, and that's the path the particle will take. To minimize the difference of the two. That's called the action. And the amazing thing is it's completely equivalent to Newton's laws, F equal ma and all the rest. So all you have to do is say a particle will go from here, a football, a baseball, will take a trajectory that every point minimizes the difference between its kinetic and potential energy. And that was the principle that Feynman said he fell in love with in high school. It amazed him about motion. Of course, he actually forgot about it pretty quickly. When he was in university, he entered MIT as an undergraduate, and one of his friends, Welton, basically said every time in classical mechanics classes that action was mentioned, and this quantity here is called Lagrangian, was mentioned, Feynman would ignore it. He said, I just want to use Newton. I want forces. I want things I can understand. Things I can understand. So even if he fell in love with it, it was a very fickle love because he forgot about it very quickly. But he also fell in love with several other things. Let's see. Well, this is something else he fell in love with. As he began to think about physics and learn the fundamentals of physics, a paradox arose. It's a paradox that was known since the time of Newton almost. And in this case, it's something called the self-energy of an electron. If I think of an electron as electric charge, a ball of electric charge, it has an electric field around it. Now let's think how you make an electron. Let's just imagine an electron as a ball of charge, and I put it together by bringing charge in from infinity. Well, I bring this one charge in, and then I bring a little more charge in, but as I bring it in, those charges repel each other. It takes energy to bring them together, and I bring another little bit of charge in, it takes more energy. Now it takes a finite amount of energy to bring all that charge together if the electron is a finite-sized ball. But if the electron is a point particle, which is what we're told in classical physics, then it takes an infinite amount of energy to bring all that charge together, because all those negative charges repel one another. And so the electron should weigh an infinite amount. And this was a problem that had been around for hundreds of years, but it bothered Feynman as an undergraduate, which showed how deep his thinking was. The kind of thing most people don't worry about as undergraduates. But it bothered him, and he wanted to solve that problem. And it was a problem he said he fell in love with and kept with him through, as you'll see, much of his life. He eventually won the Nobel Prize for solving the problem. He also fell in love with something else as an undergraduate. His wonderful wife, his first wife, who he met as in a high school. In fact, before high school, he used to be a family friend, and she was, and I can now say this because I know what it's like. She was everything he needed as a human being and as an intellect. She was the complement to him in every way. She was cultured, he was not. She was brave. Well, he was brave, but she encouraged him to be brave. In fact, the title of one of his books, Why Do You Care What Other People Think, is a famous sentence that she told him later on. Actually, they still weren't married when he was in graduate school. He used to work for John Wheeler, as I'll talk about. And she had a pet name for him, Putsy, it was called. And she made him some pencils engraved, I love you, Putsy. And she caught him one day scraping off the engraving because he was worried about Professor Wheeler seeing it. And she scolded him. She said, "What do you care what other people think?" And I think, ultimately, that early love that he had for her that was validated, I think helped contribute to the courage that he had later on to always go his own way. It was a natural characteristic of his, but that support that she gave him at a crucial time in his life, because graduate school is a very insecure time for anyone who's been in graduate school, at least it was for me. And the fact that she gave him the courage and the confidence to go about his own work, I think was essential in forming the man that eventually became Richard Feynman. And it was clear to everyone that by the time they were undergraduates, they would be married. And they decided before he went to graduate school that they would indeed get married, but not till after he got out of graduate school. And after MIT, he got actually an offered admission to Harvard right away without applying, because he finished first in something called the Putnam examination, which is a national mathematics competition. If anyone's ever taken the Putnam exam, you know it's impossible. Many people get no answers correct among the best mathematicians in the country. Feynman got not only number one in the country, but a score that was basically unheard of, which is another fact that people, and Feynman used to play it down. He was an incredible mathematician. His mathematical ability was almost unparalleled. He pretended often to not know mathematics in a way, but he was an unbelievably skilled mathematician. But he didn't go to Harvard. He ended up going to Princeton. He almost didn't get into Princeton. The department discussions about Feynman consisted of three things. There was a departmental discussion. He took the exams to get in, and he scored the highest on the physics entrance exam that anyone in history had ever scored. He scored the lowest in English that anyone they'd ever considered admission of. And there was a big debate, should we let this guy in? And happily they did. They also almost didn't let him in because he was Jewish. There was a quota on Jews. And if you read, the chairman of the physics department at Princeton wrote his professor at MIT just saying, just how Jewish is he? Which is kind of amazing because Feynman, like most scientists, was an atheist. But it was just, but in any case, happily, that nonsense didn't prevail, and Feynman made it to Princeton, where he was lucky enough to work with a young assistant professor, John Wheeler. John Wheeler is a delightful man. As I say, I got to know him as well. A gentleman, a true gentleman, but also brave in the extreme, and the most important thing, absolutely crazy. Just as crazy as Feynman. And that was the important thing, because neither of them were afraid of telling the other their crazy ideas. And that was very important. Because rather than say, that's crazy, I won't think about it, when one said to another crazy idea, they'd say, let's see how crazy it is. And Feynman had an idea that he told him as an undergraduate. He said, well, I can solve this problem of the self-energy of the electron if I just get rid of electric fields. Let's say electric fields are really, which were invented by Faraday, are just really not there. Let's say every electron in the universe interacts with every other electron without any fields in between. Its motion is determined by the motion of every other electron in nature. Now, normally, if you were to say that there are no electric fields, when of course electric fields are the basis of modern physics, the professor would say, go home. But Wheeler didn't. Wheeler said, well, what would be the implication if you got rid of the electric fields on an electron? Is that possible? And he said, well, there's a problem. If the motion of one electron is determined by the motion of and the behavior of all other electrons in the universe, well, it takes time for this electron to know where the other electrons are. So as this electron moves, the force it feels will be delayed in time because all the other particles, it'll have to know where all the other particles in nature are. Well, you think that would be enough to kill the idea. But Wheeler said, no, well, that's a problem. But what if the interactions go backward in time? Well, then would it be able to work out? And he gave Feynman the problem and said, would this theory work if all electrons are affected by all other electrons and the interactions go sometimes forward and sometimes backward in time? And Feynman worked it out and found out if half the time the interactions go forward in time and half the time the interactions go backward in time, you could reproduce the results of electromagnetism without any fields just because of those charges. Now, that was interesting. But already, and this was in the 1930s and early 40s, already by this time, of course, we knew that classical electromagnetism was not the relevant theory to describe nature, because nature at its heart is quantum mechanical. And so if you really wanted to solve the problem of the self-energy electron, you had to understand the quantum mechanics of this kind of situation. Now, this fact that he had a crazy idea early on that Wheeler didn't cut down is in Feynman's Nobel Prize speech. He said, an idea which looks completely paradoxical at first, if analyzed to completion in all of its details and in experimental situations, may in fact not be paradoxical. The idea is, don't give up on any idea until you can prove it's wrong. And try it in many different situations. It may be right in one, but don't give up there. Try it in lots of situations. If it fails in one, throw it out. But if it survives all of those tests, then maybe it makes sense, even if it doesn't make sense in your head. I was just having a debate with a theologian in North Carolina the day before yesterday, which I don't want anyone to watch on the web because it's just so tedious, who was arguing that, saying something was just like saying 2 + 2 = 5. I happen to have a T-shirt that says, which I happen to have on underneath my shirt at the time, and I took off and showed, it says 2 + 2 = 5 for extremely large values of 2. And it's true. And common sense, what we have as classical common sense, often should fail us, and we can't be guided by classical common sense in the real world. We have to ask, what determines what's sensible is not our minds, but nature, as Feynman repeated more and more often. Now, I want to talk about quantum mechanics for a few minutes, and because I want to show you what Feynman did. Feynman's one of his greatest contributions to science is to completely redefine how we think of quantum mechanics, and laid the basis for what eventually won him the Nobel Prize. But first I have to tell you a little bit about quantum mechanics. So I'll tell you one of the craziest things about quantum mechanics. So if I have an electron here, or if I have a billiard ball, and I throw it at a wall with 2 holes in it, and I have another screen, like this screen here behind it, what'll happen? Well, the ball can go through either of these holes, and I'll get sort of dirt marks here and dirt marks there where the ball can hit, right? But if instead, so there you go. If instead I don't take a ball, but I have a wave, like a water wave, and I let it go through the same wall with these two holes in it, well, the water wave goes through both holes, and you'll find that the wave will interfere with itself. New little ripples will come along, and what you'll see are a series of lines called an interference pattern. If you've ever watched here, if you watch the waves come in on a somewhat calm day, behind a rock, let's say, see two waves come in, you'll see they'll form beautiful patterns of ripples. We call them an interference pattern. What happens when you throw, not baseballs, but electrons at this? You throw electrons at this wall, and the electrons are particles, just like those balls. But what do you see when the electrons go through these slits? You see a pattern that looks identical to the pattern of those waves. Now, I'm not trying to argue that electrons are waves here. I'm trying to argue that this is crazy, because electrons are particles. And you could say, this is so crazy, because what it means is the electron acts like it's going through both slits at the same time, because that's what a wave does. But electrons are particles, so it goes through one slit or another. And I can prove it. I can shine a light on these slits, and when each electron goes through, I can say which slit did it go through. And indeed, if I do that, and I send electrons in one by one, and I shine a light on them, each electron will be observed to go through only one slit or the other. And I can say, aha, I've proved it. The electron only went through one slit. But then I turn around, and the pattern has changed. The pattern looks like this pattern, with two spots, not a whole series of spots. So if I look at the electron during the process and determine which slit it goes through, the pattern is different than if I don't look at the electron. And what it means is, when I'm not looking at the electron is going through both slits at the same time. And Feynman realized that, in fact, you can understand quantum mechanics in this way, and he needed to. He was at a beer party. This is a beer party, not the same one, in Nassau Hall at Princeton. And he was asking, he realized he still wanted to solve this problem of self-energy of the electron using quantum mechanics, but he couldn't use quantum mechanics. Because the quantum mechanics of the day said, well, if you give me a system at one time, I can calculate its behavior at all later times. But in his model, he had an electron, and it depended on the motion of all electrons at all times. So he asked this German guy who was visiting, he said, do you know of anyone who's ever formulated maybe quantum mechanics in a way that depends upon the paths of particles? And this guy, Herbert Yale, said, I think this guy Dirac wrote a paper on this subject. And so they went together to the library. This is the physics library at Princeton. And they found Dirac's paper from 1934. I can't remember. 32? Oh, yeah, okay. Where he had in fact argued that you might use the action principle to describe quantum mechanics. The famous action principle. The fact that, remember, classically, the action of a particle as it moves is a minimum in any trajectory. But he argued it, but he didn't prove it. And the interesting thing is, Feynman was there with Yale, and they looked at it, and Feynman proceeded right then and there to work out a specific example and prove that it worked exactly, that the approximation or the inference that Dirac made in the paper was actually true explicitly. And Herbert Yale said, boy, these Americans, they're always so practical. But it was amazing. Here was a graduate student that had just proved something that, in fact, had never been proved explicitly in the literature. And that was the beginning. Feynman had suddenly gone back to the action that he'd fallen in love with as a student and left behind, because he needed it. Not because he liked it, but he needed it to solve this problem of this theory of his and Wheeler's. Now, the Feynman-Wheeler theory, which he wrote down, and he developed this quantum mechanics to explain, turned out to be not to be the right theory of nature. But the picture of quantum mechanics that he established as part of it did. By the way, here's a picture of Feynman and Dirac. Dirac was a hero of Feynman's, which is rather fascinating, because I'll talk a little bit about Dirac in a second, because no two physicists could ever be more different, which is another thing I like to stress. Everyone has this stereotype of scientists, and the stereotype is wrong, because scientists come in all types. Some people think to be a theoretical physicist, you have to be a mathematical wizard. You don't always have to be. You have to be a nerd. You have to be inward. You have to be socially inept. You don't have to be any of those things. Some of my colleagues certainly are all of those things. But it takes all types. And here were the two extremes, Feynman and Dirac. But Feynman realized you could understand quantum mechanics by literally saying that I could consider the path of an electron. Now, classically, I calculate the action of each path, and the electron takes only one path. But quantum mechanically, he said, I can calculate a probability that an electron will take a path based on its action, and a probability that it'll take another path based on its action. And in order to find the final probability of whether it's going to get up there, I have to consider all possible paths and add the action for all possible paths in an appropriate way. And when I do, I'll get the right answer. And that was Feynman's path integral formulation of quantum mechanics, which really now is the basis of our entire understanding of quantum mechanics. It's an intuitive way of understanding what happens. Instead of some miracle of calculating the Schrodinger equation or using matrices, here you can actually think about just looking at every single path. And you can even understand classically why a single path is chosen. If I had more time, I'd explain it. And if during the question period, you can ask. But it's a beautiful, intuitive picture, which is so typically Feynman. Now, okay. It was good enough for Feynman to get a degree. It wasn't good enough for him to do what he really wanted to do. It didn't solve the problem of the self-energy of the electron. It didn't solve the problem of the infinity. But Feynman graduated anyway, because something happened around the time he was graduating. Bohr came to Princeton and said, the Germans are working on an atomic bomb. He told it to Wheeler, who had worked with Bohr as a student. And Wheeler told others, and of course, as many of you know, Einstein wrote to Roosevelt and said, there's a potential of building a weapon of unprecedented destructive power, and the Germans may be working on it, we should work on it. And that thereby was created one of the most amazing projects, scientific projects, in American history. It still amazes me when I think of the Manhattan Project. It was 3 years from that letter to the time an atomic bomb was first exploded. Now, I'm not celebrating the atomic bomb. I don't by any means to. But if you think about this, in order to create an atomic bomb, you had to produce all these isotopes of uranium that didn't exist on Earth, at least in any abundance. One had to build a huge plant in Oak Ridge, Tennessee. And then determine what the nuclear physics was of these things that weren't even known. I mean, nowadays it would take more than 3 years to get the environmental permit to build the plant in Oak Ridge, Tennessee. But in 3 years, by mobilizing the best minds in the world that were available, the United States did that, and Feynman was one of the best minds. And it was the best possible thing that could have happened for Feynman and Arlene. Richard and Arlene got married just after he graduated, in spite of the objections of his parents, because Arlene had come down with tuberculosis. And Richard's mother, being a protective Jewish mother, was very concerned that the dealing with a sick wife would get in the way of his career, and he wouldn't earn enough money to take care of her. And it's really heart-rending to read the day they got married. He borrowed a car from a friend, put a mattress on the back of it because she could barely walk, brought her down to the Justice of the Peace near Princeton. They got married, and then he took her to a sanitarium for poor people, and where she stayed. Now, if the war hadn't intervened, Feynman and Arlene would have gotten a job as a professor somewhere, and they would have gone to a community and lived a standard, boring professor's life. And I think, the war was awful, but one of the nice things about the war was it changed their life. Because, as I'll tell you, Robert Oppenheimer, who ran the project, was told about Feynman and invited Feynman to be part of the Manhattan Project. And this was an adventure. The two of them had never been west. And Arlene was nothing, even though she was ill, she just thought this was the greatest adventure. And she wrote some beautiful letters to Richard about how lucky they were to be able to go on a trip. And the two of them headed out to Los Alamos. Here's Oppenheimer with Leslie Groves at the site of the Trinity explosion. Feynman was invited out. He got the very first long-distance call of his life when Oppenheimer called him and invited them in. He and Arlene took the train out on a wonderful, wonderful journey together, and it was great for them. Arlene died a month before the atomic bomb the Trinity explosion. But their life was an adventure. And I just am happy for the two of them that the last 3 years of her life, 2.5 years of her life, was not spent in some boring place like Princeton, for those who've been there. that they had that adventure that the two of them really wanted. And it was really difficult. She had to stay at a sanitarium, and the nearest sanitarium was 100 miles away. Oppenheimer had found it. He was wonderful that way. And every weekend, Feynman, who didn't have a car, would hitchhike 100 miles to spend the weekend with her and then hitchhike back. And in fact, it was near the final days of the bomb when she was dying, and he hitchhiked down and got there in time to get there just before she died. And another typical Feynman story. I know I'm going too long, but I'm going to go about 5 or 10 more minutes. Well, maybe I'm not going too long. I don't care. I'm going to go as long as I go. She died, and he was at her side, and then later on he took her clock, and her clock had stopped ticking the moment she died. Now, a lesser person would say, cosmic. There's something in the air. It's meant to be. But Feynman sat down and thought, you know, the nurse probably picked up the clock to check it, to record the time of death, and it was an old clock and probably it stopped working when she picked it up. So even then, even in the moment when the greatest love of his life died, he refused to be confused by nonsense. And you know, he used to, this is an aside, I wouldn't tell, but I don't even know if it's in the book, but Feynman realized that the easiest person to fool is yourself. And that was incredibly important. And he had no tolerance for people who fooled themselves, especially experimentalists. Fred Reines, who was later a Nobel Prize-winning physicist, probably didn't get the Nobel Prize for an extra 10 years because he was performing an experiment on neutrinos and came up with a result which Feynman looked at and said, this is nonsense. I can prove it's nonsense. And at a public meeting, humiliated Reines. And I think I probably did contribute to his being delaying getting the Nobel Prize. But Feynman used to go up to people and he'd say, you won't believe what happened to me today. You just won't believe what happened to me. And people say, what? And he'd say, absolutely nothing. Because people, you know, you have a dream. You have 1,000,000 dreams that are nonsensical. One night you dream that a friend is going to break their arm. The next day they break their leg. And you say, oh, I'm clairvoyant. But you don't remember that most of the time you dream nonsense. We all think everything that happens to us is significant. A lot of the time it's just an accident and coincidence. And you have to realize that you have to second guess yourself more than anyone else. An important characteristic. That was an aside, but I thought it was worth telling.